Acid-base reactions. Acid-base reactions are reactions that form water upon mixing of an acid and a base. For example, if we have the strong acid hydrochloric acid and we mix it with sodium hydroxide, we end up getting water and sodium chloride. You might ask, how is that? Well, hydrochloric acid is, when it dissolves in water, it breaks apart into aqueous H plus aqueous chloride ion sodium hydroxide, being a strong base, does the same thing. It breaks apart into its sodium aqueous sodium ion and aqueous hydroxide ion. Okay, those go together to form H2O liquid plus sodium ion plus chloride ion. Now, things that occur on both sides of the reaction equation can be canceled. So chloride ion occurs there, chloride ion occurs there. It's aqueous, it can be canceled. Sodium ion occurs there, sodium ion occurs there, it can be canceled. So what are we left with? We're left with H plus aqueous plus OH minus aqueous gives us H2O liquid. This is what is called a net ionic equation. Let's look at more examples. So in acid-base reactions, they're also called neutralization reactions. Generally, we form water and an ionic compound called a salt that remains dissolved in the solution. And the net ionic equation, as we've seen already, is H plus OH minus gives H2O liquid. Some common acids and bases that you need to know. You need to learn these from table 7.3 in your book. You need to know these common acids and bases. Okay, let's look at writing the acid-base neutralization reaction when sulfuric acid and potassium hydroxide are combined. Okay, so let's write the molecular equation first. First we write sulfuric acid, H2SO4. Okay, and that's AQ. Alright, then we're going to write potassium hydroxide. Okay, that's dissolved in water, so it's AQ. We're going to write our reaction arrow to produce our products. Now our products are going to be where we switch partners. So potassium gets sulfate and hydrogen ion gets hydroxide ion. So we end up with potassium sulfate and HOH, which we also call water, H2O. Okay, so you see they just swapped partners. Now we need to make sure we balance the equation, so we need a 2 there for 2 potassiums. We need 2 hydroxides, so that means we need to put a 2 here, and that's 4 hydrogens. We have 4 hydrogens over there, so it's balanced. Now it's pretty tedious, but we need to write a complete ionic equation. So everything that's aqueous in this equation, this is aqueous too, I forgot to write it, gets written as its separate ions. So we have 2H plus aqueous Then we have a sulfate, aqueous. Then we have 2 potassiums that came from right here, aqueous. And we have 2 hydroxides. 2 hydroxides that are aqueous. Okay, these yield 2 potassiums that are aqueous and 1 sulfate that is aqueous. And 2 waters, which are liquid. Okay, now you can't write anything that is a liquid, a solid, as a gas as is separate ions. So now we look at our complete ionic equation and we cancel anything out that occurs on both sides. So for example, 2 hydrogen ions do not occur over here. Sulfate ion occurs here and occurs here, so it cancels. Potassium ion occurs here and occurs here, so it cancels. Hydroxide ion occurs here, but it occurs in water over here, so it can't cancel. Now all we do is come down and write down our leftover species. Yields 2 waters. Okay, so that is called our net ionic equation, except these 2's, actually we don't need them, so our 2's we can actually become 1's, and so we just need H plus OH minus gives 2 H2O's. But we do need our aqueous signs. Okay? Let's look at another example. Write the acid-base neutralization reaction which occurs when nitric acid and calcium hydroxide are combined. So nitric acid is HNO3, it's one you have to know. And calcium hydroxide, that's calcium hydroxide, we would have to have 2 of those. Okay, these are aqueous. When they're combined, we have a swapping of partners, so calcium gets nitrate, hydrogen gets hydroxide to form H2O. And the salt that forms is calcium nitrate. And that's aqueous, dissolves in water. Okay, so now we're going to write our complete ionic equation. So H plus aqueous plus nitrate aqueous plus calcium hydroxide, so calcium 2 plus aqueous. Oh, I forgot to see if it was balanced. Nitrate's 2, nitrate's 1. Uh-oh. We need to put a 2 there. So that gives us 2 hydrogens. 2 hydrogens, oh, you 4 hydrogens. So we need a 2 here to give us 2 oxygens, and now it's balanced. So that means that we need to squeeze a 2 in right here, and a 2 right here. And we've got 2 hydroxide ions. it came from this aqueous calcium hydroxide, yields 2 water molecules, or moles of water, plus calcium 2 ion, AQ, and nitrate ion. AQ. And how many of those? We had 2. So we have to squeeze in a 2. So notice that our hydrogen ions don't cancel because they become water. Our 2 nitrates do cancel. Our calcium ions cancel. Okay, so what we're left with then is 2 hydrogens plus 2 hydroxides gives 2 waters. And when you go through, you can convert these to ones, ones, ones. We really don't need those for the net ionic equation. So that's the net ionic equation for that. Okay, some acid-base reactions occur and produce what are called intermediate products. Okay, so some intermediate products that you should know of that evolve gas are carbonic acid, sulfites, and ammoniums, like ammonium hydroxide. Okay, so let's look at some examples of some gas evolution acid-base reactions. Okay. Right, so if we have hydrochloric acid and potassium sulfide, that makes, when we switch the partners, we get potassium with chlorine and hydrogen with sulfide. And hydrogen sulfide is a gas. If we have hydrochloric acid and potassium carbonate, then we get, we're going to get hydrogen with carbonate and potassium with chloride, and we'll see how this forms water and carbon dioxide, how this forms water and SO2, and how this forms water and NH3 in just a second. Okay, so some gas evolution reactions. If we have nitric acid, we react it with sodium carbonate, we get H2CO3, which is aqueous, and NaNO3. If we want to, we need to recognize that this is one of those species that decomposes, and it decomposes into water and carbon dioxide gas. So we need to finally balance the equation, so we can put a 2 here and a 2 over here, and that gives you a balanced equation. Okay, let's write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid, so HBr, and aqueous potassium sulfite. Okay, and that goes to yield, so potassium is going to get bromine, and hydrogen is going to get sulfite. So we're going to make this hydrogen sulfide okay, which is aqueous, but, and we're going to make potassium bromide. But this immediately decomposes into water, H2O liquid, and SO2 gas. And that's just that table that you need to learn. So if we want to write a full ionic equation, then we write everything out separate that's aqueous. So hydrogen bromide is aqueous, H plus, AQ, plus Br minus AQ, plus 2K plus AQ plus SO3 2 minus AQ. Now this is going to yield H2O liquid, which we cannot write as a separate species, SO2 gas, and K plus, aqueous, and bromide, aqueous. Okay, let's go up here and see if it's balanced, because I forgot to check whether it's balanced. We've got 2 hydrogens here, and we've only got 1 there. We've got 2 potassiums there, so we know we're going to need to put a 2 there. We're going to need to put a 2 there, so we have 2 hydrogens, 2 bromines, 2 potassiums, 2 potassiums, 2 bromines, 1 SO3, so now we're balanced. So we need to come down here and change this to a 2, this to a 2, and we need to change this to a 2, and this to a 2. Now, scratching out things that occur on both sides, bromines occur on both sides, potassiums occur on both sides. Those are the spectator ions. So all that is left is 2H plus, aqueous, plus SO3, 2 minus, aqueous, yields H2O liquid plus SO2 gas. So that is what is called our net ionic equation for that reaction.